In this video, we will see an example of a FMU customization and we will run it with the example of the kuka robot. First, we will create a custom FMU. Then, we will set up the 3D experience environment to link the FMU to Dimela behaviors. Finally, we will run the simulation. Let's create a custom FMU. This FMU will generate a ramp command for the virtual robot, but any other behavior can be created. Open the blank Visual Studio project by opening the SLN file. This FMU already has 6 input and 6 output to read and write the 6-axis of the robot. The behavior is blank. We will modify the FMI component.cpp file. Let's add some global variables. Iter will count the number of iteration from the start of the simulation. New pos will store the target position. The robot will move between 2 positions, the 0 position and the target position. Step will count the number of iteration for the generation of the command. Ramp is a function that gives the value of a ramp signal according to the start value, the end value, the current step, if the ramp is discretized into 1000 values. This function is vectorized to generate the 6 independent signals for the 6-axis of the robot. In the initialization of the FMU, the 6 outputs of the FMU are set to 0. This is done with the setOutput function, which takes the ID of the ax, from 0 to 5, and the value to be set. Then, let's create the behavior that will be executed at each step of the simulation, in the computeStep function. The iter variable is incremented. To avoid any problems, don't do anything while iter is less than 2. We will then create a cyclic command, move from the 0 position to the target position, wait a bit, move back from the target position to the 0 position, wait a bit. Repeat the cycle over and over. The cycle will be controlled by the step variable, which will increase from 0 to 4000 at each step, and will go back to 0, and increase again. When the step variable is less than 1000, the robot will move from the 0 position to the target position. For that, the ramp function will store the current position, according to the step variable, into the cur variable. The output of the FMU is then updated to the value stored into the cur variable. When the step variable is between 1000 and 2000, don't do anything, expect increasing step because we don't want to create any infinite loops. When the step variable is between 2000 and 3000, the robot will move from the target position to the 0 position. For that, the ramp is generated with slightly different parameters than the previous one and with the target position as offset. The outputs of the FMU are updated like before. When the step variable is between 3000 and 4000, don't do anything except increment the step variable. Finally, when the step variable is greater than 4000, it is set back to 0 to start again the cycle. Let's compile the code into a FMU file. For that, click on Rebuild. If succeeded is written, then the FMU file is created in the root folder. Let's launch the functional and logical design app from the dashboard. Make sure that the interface's language is in English and that the background is white. Insert a new logical component. Click on Logical Reference. Do the same twice in the green block that just appeared. Let's add a Dimela behavior to a block. For that, click on Insert New Behavior, then on Dimela Behavior. Double-click on Main Model to get inside the block's behavior. Drag and drop the kuka kinematics class. Exit app to go back to the logical blocks. Select the other block and click on Import FMU. Select the FMU created before. When the FMU is imported, inputs and outputs appear on the block. Connect the FMU outputs to the Dimela behavior block. Click on OK to confirm the connection. When the other window appears, click on Cancel. Go back inside the Dimela behavior block. Connect the inputs that appeared to the inputs of the class. Exit the app. Let's import the 3D model of the robot that is connected to the Dimela behavior kinematics class. Right-click on Physical. Insert Existing Product. Search for the 3D model and select it. It will then be displayed. To hide the lines and planes, click on View, and on View Modes. Disable points, axes and planes and wires. Double-click on the logical reference in the tree to get back to the logical blocks. Now, let's set and run the simulation. Access the properties of the FMU block. In Execution tab, select with delay. In Simulation Setup, make sure that Interactive Simulation and Infinite Simulation are enabled. Run the simulation. In View, change Active View, you can move the logical blocks to see the simulation. The FMU creates the input values for the robot's kinematics. Let's summarize what we have learnt during this video. First, we saw how to customize a FMU from a blank skeleton. Then, we saw how to integrate a FMU in 3D Experience. Finally, we ran a simulation combining both FMU and Dimela behaviors.